because essentially what we're doing is we're figuring out percentages. So for example, if I gave you CO2, and why would I have a good pen? That'd be crazy. If I gave you CO2.
Are we supposed to write the thing in green?
No. If I give you CO2, and I were to ask you what percentage of CO2 is carbon and what percentage of CO2 is oxygen, they sometimes say instead of percent, they say percent by mass. And what they really mean is percent by molar mass. Because if we take a look at this, and we understand this, hopefully, couldn't I figure out the percentage of girls in this classroom simply by taking the number of girls and dividing by the total number? Right? I can take the number of people with no hair versus people that have hair. It'd be 1 to whatever, 15 or whatever. There's a whole bunch of ways we can figure percentages, but it always is this: the number of whatever you're looking for versus the overall. So if I wanted to figure what percentage carbon is of this entire compound, what I probably want to do is make sure I knew what carbon's molar mass was, which happens to be 12.01. Agree? Yes. Which I get from where? The periodic table, right? But then don't I have 2 oxygens as well? And that's 2 times 16.00. So if I added it all up, 32. The overall molar mass is going to be 44.01 grams per mole. Now, why is this important? Well, if I have the overall molar mass and I want to figure out what percentage either of those other 2 things are, couldn't I take the molar mass of carbon, and for carbon's percentage, couldn't I just go 12.01 divided by 44.01? You got to times it by 100 because I'm hoping that you guys at this point of your academia understand that whenever you do want to figure out percentage, you divide something to something else and you get a decimal, right? We don't run around going, oh, I have 0.9%. We then multiply by 100 and say I have 90%. Does that kind of make sense? So if I do the math on this, and it's only because I read it in the last class, I believe it becomes 21.27%. Might be 27.27%. Can someone on their calculators divide 12.01 by 44.01? I think it's 27.2. 27.29? I'm not sure. Anyone? How about everyone? How about that being the new game? Everyone punch that in. 12.01 divided by 44.01.
0.272893.
So 0.2. Okay, so 27.29%. Okay. Now watch. Isn't carbon made up of only carbon and oxygen? It doesn't matter how many oxygens we have. We just want to know what percentage oxygen is. There's 2 ways we can do that. Couldn't we take oxygen's molar mass, which is 2 times 16, because we have to get all the oxygens? Wouldn't that be 32.00? And divided by 44, wouldn't we get a number we can multiply out? Or isn't oxygen the only other thing in this compound? So couldn't we just go 100, subtract 27.29? And what would that give us?
73 point.
Is it 73 though?
71.
72.71%? So right now, what I know is that every single carbon dioxide, every one, 72.71% of it is going to be oxygen, and 27.29% is going to be hydrogen. What does that allow us to do then? Well, if I know what percentages I have of this, and I were to tell you, hey, I have 20.0 grams of carbon, and I asked you, how many grams of oxygen are there in that 20 grams? Don't we know that 72.71% of every CO2 is oxygen? And if my CO2 is 20 grams, wouldn't 72.71% of this be oxygen? Yeah. So whenever you're asked to figure out the percentage of something, don't you take the percentage and make it into a decimal and then multiply it by that thing? So in this case right here, couldn't I go, all right, well, 72.71%, wouldn't that be 0.7271 times 20.0? What does that give me? 14.5 something.
Yeah.
So of the 20 grams, 14.5 grams of that would be oxygen. Wouldn't the remainder of it be carbon?
Yeah.
So one application of this is this. Once we know the percentages of the elements in a particular compound, we know those percentages are going to hold for every single one of those compounds. So later on, if I give you any mass of any particular compound, I will be able to determine how many grams that is. So this, where we take the compound and we figure out the percentages, it's just a matter of having a periodic table at hand. What I want to do today with you is I want to go the opposite way. I want to start with percentages of something, and I want you to come up with the formula. So this is how these problems work, and in order to do proof of concept, I'm going to use the exact same percentages we solve for here. I'm going to start with them and see whether we can work backwards and get CO2. Ignore the green right up here. Yeah? We're just going to do this problem. So, given 27.29% carbon and 72.71% oxygen, what is the empirical formula? What is the empirical formula? Now, can anyone verify for me that they have the section in my notes that walks you through the steps?
Yes. Last percent. One, pretend you have 1 mole of substance and calculate the total mole amount.
Okay, that's percent by mass. Go right down to where it talks about empirical.
Figure out the molar mass of the empirical formula.
Okay, so watch. Would you agree that they're starting us off, and we're just going to go the opposite way in this particular problem? They're starting off 27.27 grams of, or percentage of carbon and 72.71% of oxygen. Now, listen to me carefully, and this is kind of a little trick. If they give you percentages, we can't use percentages to convert to any units. So what we're going to do is we're going to start with percentages and pretend that we have 100 grams. Do you realize if I have 100 grams of something, whatever the percentage is would be the number of grams?
Yes.
So if I told you, hey, whenever they give us percentages, our first job is we're just going to want to pretend we have 100 grams. So if I pretend I have 100 grams, wouldn't that be the same thing as saying I have this, 27.29 grams of carbon? And wouldn't that be the same thing as saying I have 72.71 grams of oxygen? Now, I want you to be aware. The majority of problems you're going to solve on the test, which you're going to have next class period on this stuff, is going to start you off with percentage. But if they start you off with grams, they've saved you having to convert from here to here. Whatever they give you in grams, you just start off with here. And as always the case, do we ever use grams in our equations or anything we're dealing with? They're shaking of heads. Don't we always convert to moles? Always? So here's our steps. If they give you percentage, pretend you have 100 grams and convert to grams. If you have grams, convert to moles, because if you know the moles of each one, you now have a ratio for your equation. So let's do this together. The molar mass of oxygen of carbon is 12.01 grams of carbon for every 1 mole of carbon. Can someone do the math on that for me? Give me 2 point something. And for oxygen, it's 16.00 grams of O for every 1 mole of O. Now, can I pause for a moment here? And I want you to take a note. Do you guys see how here it's grams of O and not grams of O2? We don't know how many O's we're supposed to have. You guys follow? So you're never going to put like O2 or H2 or whatever. We're never going to do that because we're trying to find the formula. So in these two cases, did anyone do the math on the top one for me? Say it one more time. 2.27, wonderful, 2.27 moles of carbon. And in this case here, it's going to be something like, what is it, 4.56 moles of oxygen. Ta-da! 4 point what? 5.4? Wonderful. Just wait a minute, and I'll answer your question. So this is the number of moles I have of carbon. This is the number of moles I have of oxygen. That actually is the ratio. So if I wanted to, I could write this equation like this. Carbon, 2.27 Oxygen, 4.54. That's literally the ratio of those two to each other. What's the problem with this? They're not whole numbers, right? And can we have 0.27 of a carbon or 0.54 of an oxygen? So this, even though this is the ratio of the moles of each of those things in those percentages, we've got to get them to whole numbers. And so we're going to do another Jedi trick. The Jedi trick is simply this. When you've converted to moles of both things, take the smaller of the moles and divide them into both. So would you agree with me that 2.27 is smaller than 4.54? So what I'll do is I will take that and divide by 2.27, and this and divide by 2.27. Now we do this because we know automatically one of them be equal to 1. And then the other one, it's going to be some number that's going to be less ugly to work with than this. Now, I don't want to spoil this for you, but if you do this out, it's going to be, I was going to do the approximately, but isn't it equal to 2? Now, let's say it was equal to 1.99. 1.99 is essentially 2, right? Or 2.01. That's 2. So the ratio between these two is 1 to 2, right? Therefore, that's what the formula is. The formula would be CO2. Do you see how we got back to the same formula that we started with when we tried to figure out the percentages? So this is proof of concept that if they give you the percentages, you can solve for the actual formula, or if they give you the formula, you can go backwards and solve for the percentages. Now, step number 1 in this, and I didn't write it, it says, this is, what is the empirical formula? Step 2 is this. If the formula mass of the molecular formula is 88.02 grams per mole, what is the molecular formula? This can be a little bit more convoluted, so write it down and I will try and explain it to you, please.
Can I ask a question?
Yes, please.
Okay, so in the question, it was percentage for both carbon and oxygen.
Huh?
Then why, when we solve it, we have it in grams?
Because what we did is we know that there's going to be a molecule that has this percentage, right? And so our trick is we just pretend we have that number of grams of each of those things, because that's going to be the same mass ratio as this is, and then we convert to moles, then we convert to whatever.
Okay, and
So it's terribly written. If the formula mass, AK, isn't that another way of saying molar mass? If the formula mass of the molecular formula is 80.02 grams per mole, what is the molecular formula? Now, 88.02 grams per mole. Now let me explain this to you, and this is the one tricky part. If you can get this, then everything should fit into place. Are you with me? Do you realize that if I say a 2-to-1 ratio between oxygen and carbon, aren't there an infinite number of 2-to-1 ratios of carbon and oxygen? When I say infinite, I mean infinite. Wouldn't 4 to 2, 6 to 3, 8 to 4, wouldn't all of those be that exact same ratio? So if I give you these two percentages, aren't there an infinite number of carbon and oxygen combos that can give us that percentage of 2-to-1? So what we've just solved for is CO2, and that's the empirical formula. The empirical formula is the formula that you cannot divide it any smaller. Like, you know how if you have a 4 and a 2, you can divide both by 2 and end up with a 2 and a 1? When you cannot divide by a normal integer or a normal whole number to reduce the number any farther of the subscripts, you have the empirical formula. But would you agree with me that C2O4, C3O6, C4O8, C5H10, et cetera, et cetera, et cetera, et cetera, wouldn't those all have exactly the same ratio of carbon to oxygens and fit that exact same percentage? Are you with me? So what they'll often do is they'll give you percentages and then say, hey, we're looking for a molecule that has those percentages that has this molar mass. So bear with me. If I tell you that this percentage has a molecule that has this mass, couldn't I go to the original empirical formula? Isn't it 1 carbon and 2 oxygens? Right? And if they tell me the molar mass of a molecule that is some multiple of this, couldn't I figure out the molar mass of CO2 and compare it to the molar mass of what they're looking for and determine how much bigger what we're looking for is? Another way of saying it is this. Isn't 80.02 grams per mole, isn't that the molar mass of this molecule that has the exact same percentages as my empirical formula? And isn't my empirical formula, in this case, isn't it, did I say 80? It should have been 88.2. Sorry, 88.2. My bad. I know you can't erase.
Wow, right now it is.
It's supposed to be 88.
It's supposed to be 88.02. Okay. Good luck.
That's what I'm saying.
So they give you the molar mass. They give you the molecular mass of 88.02.
See you tomorrow.
So watch. Isn't 88.02 exactly 2 times bigger than the molar mass of CO2? So mustn't that mean that the formula is exactly double this formula? And I hear a bunch of you guys doing this here. Wouldn't that then be this, the molecular formula we're looking for, isn't it C2O4? Because it's exactly double. If this number had been triple this, wouldn't it be C3O6? Do you guys follow how this works? So what's kind of cool about these problems is every single problem, when they want you to find some sort of molecule, your first job is to get to the empirical formula. Once you have the empirical formula and they give you the molar mass that they're looking for, it's going to be some increment of what the molar mass is of the thing you found. Are you with me? So, incidentally, what they'll sometimes do is they'll say, hey, what's the molecular formula for this that has a molar mass of 44.02 or 44.01? Well, isn't the molar mass of that the same as the empirical formulas? So the molecule they're looking for could be the empirical formula. You guys follow what I just said there? So let me recap. Every time they give you percentages of elements in a compound, stay with me. Anytime they give you percentages of an element in a compound, your first job is to convert that to grams. Once you have grams, you're going to convert to moles. Once you have moles, you do the Jedi trick of dividing by the lowest number. And then hopefully these numbers are whole numbers. If they're not, we're going to have to make them into whole numbers. So let's try one more problem. The one in green is the problem we're going to solve right now. So everyone write the number in green. And can I get a volunteer to help me write? That's decent handwriting.
I'm just going to pick up the worksheets if you're going to record, right?
It's recording and the worksheet's on the other side of the paper. Thank you.
Right up there.
Yeah, so let's erase this. Let's erase this stuff right here, and we're just going to solve for this on the board. And I want you guys to all kind of work along with her as she does this problem. But good luck, guys. I am recording the video for today. Can you see that it's centered on that? Can you see yourself in that? Okay. So just like our previous problem, aren't they giving us the percentages of the elements that are involved? Yeah? What's our first step when they give us percentages? Pretend we have 100 and convert it to grams. So can you write all 3 of those as grams and make a little table for them, please? We got to use molar masses, right? So can you put on the underneath on grams?
Do you have a periodic table?
Let's just use 16.00. I'll help you with the molar masses. I've done this a few times. Good. For hydrogen, let's do 1.008 grams. And then for carbon, let's go 12.01. Okay, so we've now set it up so we can figure out the moles of each one. Can someone mathematically, can you guys all pull out calculators and help her with that, please? Definitely need help.
Paper towels.
Turn the box over.
The first one is 4.04.
Good. Right moles.
2.7. The very bottom is 2.7.
The hydrogen is 8.103.
Okay. You realize that right there, those are the actual ratios of each of those things, right? But they're not whole numbers, are they?
Yeah, it's 8.
So to get the whole numbers, well, one of them is close to it, right? Yeah. 8.10 though is not an 8, right? It's a little different. So what we do is we divide all of them by the smallest number. This is our Jedi trick like we did before. You look so contented holding the baby like that. So can we divide all, what's our smallest number? 2.7. So let's divide them all by 2.7.
That's first one is 1.5.
Wait,
So
what?
carbon is 1.5.
The first two.
4.1?
No, 1.5.
No, you're fine there.
No,
But when you divide it, go equals
Oh.
4.5. The next one?
One's 3. On the bottom is 1. But they're kind of about
For the
that.
first
So,
one,
So
only want to touch your phone.
So this is actually good because we went from pretty unruly numbers to 1.5, 3, and 1, right? So what will always happen is either A, all of them will be whole numbers when you divide out, in which case those are subscripts for our formula, or we have to multiply by the lowest possible whole number we can. Now, would you agree with me that I can multiply all of these by 2? And by the way, you can't just multiply one of them by 2. You have to multiply everything by 2 because the ratios will stay the same. If you multiply all of them by 2, what do we end up with?
2, 4, 6.
And they typically are pretty good. They are typically pretty good about telling you which order to write your compound in. So we're going to write C and then the subscript 3, H and the subscript 6, and O and the subscript, I believe it's 2. I can't see 3.
I have a question.
Yes, ma'am.
After you said you multiplied by the lowest possible whole number, so you would pretty much always do 2.
Yes, unless, watch, unless the number was 4.333
Is it repeating?
or whatever, right? But if you have 0.33, then you're going to probably multiply by 3. Or if you have like 0.25, multiply by 4. If you have like 0.2, you multiply by 5. That's typically the smallest we go, but you guys follow that we could multiply by different numbers.
Yeah, okay.
Does that make sense? So if I were going through this, Kat, what I would start with is see if I can multiply by 2 and get the equal. And then just go up the list. 3, 4, 5, 6. I've never seen them problems where it's more than 6, but you may have to go all the way up by 6 to get to all 3 of them being whole. Now, if you get a number and it's like 1.99, you're like, nope, not 2. Then you're gonna be, or if you get like 1.98 or 1.97, that's pretty good after you divided it. That's really close to the whole numbers. You're probably gonna be okay with that. So in this case right here, wouldn't we call that the empirical formula for these percentages? Can we divide this by any number to make it any smaller? No. This is, for those of you who are wondering, as a baby handling tip, you probably don't want to smash their head down onto the table in front of you. I mean, you could, but that would be bad for everyone. You know what they could have asked in this problem? They could have given you the molar mass of a compound they were looking for that has those percentages. And if they give you the molar mass of that compound, you're going to have to figure out the molar mass of the compound we've drawn. and compare it to the molar mass of what they're giving. And in those cases, it's almost always going to be some pretty low multiple, 2, 3, 4, 5, etc. Or it may be the same number as the molar mass. So unfortunately, once you've figured out your empirical formula, you're probably still going to have to figure out the molar mass of it to compare to the molar mass they're giving you in the problem. Now, that's the lecture for today's class. What we're doing, and that's the last content that's covered on the test. So what I've given you is I've just given you a worksheet that practices doing empirical formula, molecular formula. If you can do these, you'll be able to do the 2 or 3 examples that you're going to have on the test. The answer key is sitting over there on the second table, I believe, unless someone's moved it. But I want you to partner up in groups, and if you cannot do this during this period of time, we have, what, 30 minutes in class, maybe more, 35? Come up here on the board and let's do them together. Yeah? Can you hit the stop broadcast and just have me